Hello and welcome to another episode of the Oxford Online Maths Club. My name's James and today the episode's called Solid Gold, and we've got a shell and a block of gold in the thumbnail on YouTube, so something's going to happen. Hi to people who are watching live. Chat's doing something a bit funny there. I wonder if I can fix that. Maybe I can't fix that live. I'm joined today by 4.5 people in chat. Can I fix that at all? We'll see. I've got Andre, Anonymous, Shrisht, more anonymous people than I'm pretty sure I saw. Aya there as well. If you would like to join Slido chat, you can do that by heading to slido.com/OOMC, which is where we do polls like this one, asking how your day was today. How's it going? And hi to Anna and Jewel, and I got loads of neutrinos here, and yes, I think I said Shrisht. Shrisht gets a second shout out because I'm feeling like it. While you're voting on how your day was, so sunny today. It's really lovely weather in Oxford today. It's absolutely brilliant. Something about the town just looks really, the town itself just looks really good when it's got a bit of sunshine on it, which doesn't always happen. Quick look at the notice board. Still got this Jane Street Summer School on the right hand side, and Jane Street have published a new puzzle. They put these puzzles up on the puzzles bit of their website. This is one of those ones where you get clues about numbers, things like square numbers or Fibonacci numbers. Remember this one. Fibonacci numbers might come back again at some point today. Depends how things go. Fibonacci numbers. It's that kind of weird way of pointing at something. Multiples of 88 or whatever. But then there's also extra clues on the regions. So if you like that style of puzzle, there's some of those over at Jane Street. I wanted to shout out the open days because I'm getting some emails at the moment from people who missed our departmental open day in April, and I'm looking forward to the next ones in June when we've got some talks at the maths department. The bits at the maths department in late June don't need any booking. It's first come, first served. We're going to get as many students in the room as we can for some talks that we repeat during the day on maths at Oxford. And also the attraction there is that, well, it's summer, so it's hopefully nice weather, and all the colleges are open for people to have a look around the colleges as well, with usually student ambassadors present to help people look around and maybe some information about accommodation and things like that. Okay, that's the notice board. How are people's days going? About 4 or something. Yeah, good. Rory in chat, who is, I think, Rory the moderator, says city, James, which, what are you telling me? Oh, I said town a lot. I said town, and Oxford is a city. Rory is reminding me that we have city status around here. Good. Shrist today used the sun to burn stuff with a telescope because it is that hot. And anonymous person's had half a day off. It's going great. 4.1 is pretty good for us. Okay. I have a poll. I have a second poll. Yeah, hello Rory in chat. I have a second poll, which I'm going to flip to you straight away. It's a ranking poll because Slido lets me do those. Sometimes we come into an episode and it's something totally fresh. I've got a blank slate. I want to tell you about I don't know, calculus of variations or something, and you've never seen it before. But sometimes I'm building on something that you've maybe seen before, and it's given me to get a sense of where these things sit in your mind. So I've got a vote going in chats at the moment. 3 or 4 people are ranking. We've got constants pi, e, and phi. Now, possibly you've never heard of these numbers or don't have any strong opinions, and that's fine. You can just watch the voting happen, I guess. But possibly you do already have opinions about these numbers. And part of the fun for me is to see whether pi gets a bonus for being, to do with circles, or whether it gets downvoted by people who are angry that I haven't put tau in the poll. Let's not start that one. Oh, that's just asking for it in chat, isn't it? Hi, Oscar. No, chat's lovely. Chat is very nice. Something I like about chat. You might have heard me mention just now we have current student Rory moderating chat, but something I like is that you really make Rory's job easy. Everyone chats pretty nice. Good. We did see a little bit of. No, we're good. Not the town people, says Neutrino. Oh, okay. Apparently an A-level paper, an international A-level paper that's leaked. I don't know anything about this. But Somebody's telling me about that in chat as well. I'm not sure I can help you. Aya's got Fire's the golden ratio is number 1. Should be number 1. And I'm not going to tell anyone how to vote. Are we still voting? I think we're good. I think we're good there. Fire's come last. And I think my aim today, in an episode called Solid Gold, is to try and convince you that the golden ratio is better than E and pi. I'm not saying that that's what I believe, just that my plan today is to try and convince you that is the case. Yeah, where's I? I think you mean, where am I? Oh no, yes, no, you're asking for the complex number I to be in chat, to be in the poll. Yeah, chat loves complex numbers. Okay, let me motivate this by showing you a bit of a Eurovision song. It's Eurovision this week. Here. So, okay, I want to show you this. So this is Australia's entry for Eurovision this year. And first off, yes, Australia, Europe, Eurovision, Australia. Yeah, it's been like this for a while. I have a map that I stole off Wikipedia. Australia's been in Eurovision since 2015, and partly because they just really like Eurovision, and it's nice to have people who really like being in Eurovision. There's other boxes around the edges for other countries that are in Eurovision as well. This is a color-coded map for how long people have been taking part in Eurovision. It's interesting, isn't it? You can imagine modelling that with some sort of, like, I don't know, diffusion model or something that has somehow already reached Australia. New Zealand next, right? Good. Okay, I have 2 more episodes convincing you the other 2. It's only fair, isn't it? It's like a hustings. Okay, so I want to play you just 20 seconds of a Eurovision song. I think I can do this. I think we have the technology. Let's see if I can make this work. I'm going to have 1 attempt. Come on, my road. I descend to the center of the earth. So I'm basing an episode of Maths Club around the lyrics of this song, because it's my show and I'll do what I want. Here are the lyrics on screen, and there's a couple of interesting moments in here. One, you'll have noticed the lyric, spill the tea on reality, and the 0.618, pow. I think we all wish we had the power to, get to the end of a maths calculation, say 0.618, and then pow, question done, bam, light show explodes. It's happening. So I want to explore that. The presence of some sort of random number in a Eurovision song has been commented on by other people, and I guess what we're doing is being part of the topical discourse on this matter. There's also a reference to a spiral, which I want to talk about as well. Here's the thing. In interviews, the people who sing the song, Electric Fields, talk about the golden ratio, which I had in my poll just now as this number, sometimes written as phi, of 1.618. And okay, theirs is like phi, so phi minus 1 is 0.618. More about this sort of thing in a moment. And it's the number that I want to try and convince you today is worth its weight in gold. Absolutely brilliant. Let me give you some properties of this number. And I think I want to start with it as a number before we move on to spirals or spilling the tea on reality. Let's go. So the property that it has, I'll put fact. Phi squared is phi plus 1. That's a cool fact. And I mean, it's not true in general that when you square a number, you get 1 more than the number. But this number, if you square it, you get 2.618, which is kind of nice enough to start off with. If you like, then this is the definition of phi. Well, I mean, not quite, right? Depending on where you are in maths at the moment, you know how to solve equations like this. This is a quadratic equation, so you can, if you know the quadratic formula, you can move things around and solve, so moving things onto the left with some subtraction. You can solve this to get 1 plus or minus oh, this is the discriminant is b squared minus 4ac 5 divided by 2. There's two solutions here because it's a quadratic. One of them is 1.618 and the other is minus 0.618. So actually maybe they're singing about that one. Maybe the 0.618 is like the negative root of this quadratic. I think I'm going to assume that it's phi minus 1 instead. Yeah. So then there's the question, what about other properties, right? We can all do this thing where we make up an equation and then you find the solutions and you give them a name. I don't know, maybe I should try and name my own one, right? But I've just found out in chat about the super golden ratio. X cubed is x squared plus 1. That's kind of cool. Maybe there's another one called the plastic ratio, which something x cubed is x plus 1. That one makes the mistake of being named the plastic ratio, which is not as cool. So yeah. Hi Maya. Maya's just joined and wants to know what's going on, and I think everybody else watching is in the same state of wondering what's going on. Hi Maya. Quick recap. There's this Eurovision song that I like. It's from Australia, who get to be part of the Eurovision now. And their song has this reference to the number 0.618, and all their interviews they talk about the golden ratio. So now I'm talking about the golden ratio. That's all that's going on. It's this number that has phi squared is equal to phi plus 1. So something I like about that is you can go further. So you can go to phi cubed, which would be, I guess, multiplying by phi. This would be phi squared plus 1. Which is fine, I suppose. Pretty similar. Phi squared plus phi. I've got to multiply by phi. Multiply everything by phi. That's kind of fine, except you can simplify this because phi squared is still equal to phi plus 1. So this simplifies down nicely like that. So you get this more, I guess, mysterious looking thing that phi cubed is 2 phi plus 1. I was 1 over phi 0.618. That sounds true as well. That sounds true. That sounds very true. Let's try dividing this by phi. Phi is equal to 1 plus 1 over phi. Oh, brilliant. Yes, okay, so 1 over phi is phi minus 1. Okay. I like that a lot. Okay. Thank you, anonymous person. Wants to go along the periodic table because there's also a silver ratio. I can never remember what the silver ratio is. It's not the other root, is it? No, because that's just 1 over phi. You don't get to beat the silver ratio just by being 1 over the golden ratio. That's no good. So you can keep going like this in this pattern of multiply by phi and then simplify. That would be this phi squared is phi plus 1, so we would now get 3 phi plus 2. So that's quite nice. And then phi to the 5 would be multiply by phi and simplify to be, can I do this? 5 phi plus 3. And then phi to the 6 would be 8 phi plus 5. And so on. So that's quite nice. Oh, is the silver ratio sorry, in chat. Chat's telling me about other constants. Maybe we should put these in the poll as well. The silver ratio is just 1 plus root 2. That doesn't spark joy, I'm afraid. Right, okay, fair enough. 1 plus root 2. Okay. I will take this like grassroots support for silver ratio if you can tell me some cool facts about the silver ratio. We've got 45 minutes. I'm going to convince you, you're going to convince me. Here we go. Oh yeah, so you spotted something going on here, right? I said and so on. I guess there's this rule about what's going on. That when you multiply by phi, you get a phi squared, and the phi squared always appears here, and you get a phi, and the phi always appears here. And then you always do the same sort of simplification, where you replace that with an 8 phi plus 1, for example. So the new large number on the left is the sum of these two, 8 plus 5. And this one is the previous large number from this constant here. And you've seen these numbers. God, you only get prime numbers as the constants. Well, no, because you've got 8, but also no, because these are the Fibonacci numbers. It's good pattern spotting that most of them are prime, but then yeah, we hit 8 and also hit interesting numbers like 144. They're Fibonacci numbers. Ah, wait. Do Cambridge-style number crunching, calculate phi to the 9. That turns out to be easy, because phi to the n then is just something like, now maybe I should be really careful with my numbering, but I think it's just fn phi plus fn minus 1, where fn is the nth Fibonacci number. It's about 1 in 8 that I spell Fibonacci correctly. We're going to go with it. Apologies to Fibonacci. And I guess Fibonacci is a name, so it's possibly your name too. If your name is Fibonacci, then I'm sorry to you as well. Yeah, look at that. Oh, you got a minus sign. Oh, why have you got a minus sign? Now I'm scared. I've got a plus sign. Oh, the silver ratio's got a fun continued fraction. So you can play that game. Yeah, Shrista spotted the Fibonacci numbers turning up here as well. And Aya has checked out Gabe's claims about the silver ratio. Wait, William tells me there's loads of these. A sequence of them. Okay, I need to look that up at some point. Okay, this is kind of cute. This shows you that powers of phi have something to do with Fibonacci numbers. Maybe we can do better. Can we do better? Yeah, I think we can do better than this. Let's go the other way and see what happens if we go the other way. I want to do this in parallel, so I think I should do it over here. So what do I need? I want things like 1 over phi. How am I going to get that? I think I'll rearrange it to say 1 at the top is phi squared minus phi. And then I can divide by phi, and I'll get 1 over phi here. And here's the first thing that we saw, phi minus 1. And then 1 over phi squared is 1 minus 1 over phi, but I know something about 1 over phi. 1 over phi was equal to phi minus 1. Okay, so this is feeling a little bit similar. Any guesses in chat as to how this is going to continue if I keep going? There's this thing again where I divide by phi in each row. Oh, I think I want to list the phi term first for consistency. Maybe I do, maybe I don't. Take it or leave it. I think I'll keep it on the left now. Yeah, okay, I'm going to keep it this way around. Because then I can use the fact that this is 2 lots of phi minus 1. And then subtract another 1. Okay, maybe I'm not being consistent. Maybe I'm being inconsistent in a consistent manner. So yeah, so we've got coefficients like 1, 2, and 3, which you see 1, 2, and 3 in a problem, and or maybe you think natural numbers, maybe you think counting, or maybe you think there's quite a lot of 1s up here. Is it possibly 1, 1, 2, 3? Which would be a bit more Fibonacci. And the way to find out is to do 1 more of them and find out whether you see 4 or 5. I mean, that's not proof, right? But not proof, but it's reality saying, look over here, see what's going on. Okay, so this is going to be minus 3 is 5 minus 3 phi. Okay, looking pretty good. So over here, just tidy this up a tiny bit. I want to make sure that I'm being consistent. So F3 is the one that's 2, F2 is 1, F1 is 1, and then F3 is 2 to match up here. And then this is F5 is 5, because it goes 3 then 5. Okay, that's the 3, that's the 5. I really want to make sure I'm not out by 1. Okay. Patterns? Other stuff? So there's something going on here, right, with the Fibonacci numbers. Oh, am I good enough at spotting patterns to explain what it is? Maybe I need one more. I'm trying to explain this pattern that's going on here. We see 2 minus phi, then we see 2 phi minus 3, then we see 5 minus 3 phi. It's tricky, isn't it? I suppose the number goes 2, 3, 5. Yeah, the constants of Fibonacci's numbers. Wait, Imo, is that right? You take the middle out of a regular octagon. What's the root 5 in an octagon? Oh no, silver ratio. Silver ratio, root 2. Okay, I thought you said golden ratio. I don't know why. Words don't get the same at all. Okay, so Fibonacci numbers, but maybe with alternating signs. So this is something like, so I want to say phi to the minus n is something like, is this the 4th one? This is the 5th one. No. Yeah, phi to the minus n is maybe fn plus 1 minus fn phi or something, with like a times, maybe plus or minus, maybe it all gets flipped around, so times minus 1 to the n or something. Not certain I've got that spot on. I'm worried I might be out by 1, as I so often am. Anyway, I'm pretty sure you can solve these. Yeah, here's Andre. With a minus sign. Oh, yours looks easier than mine again. The sign swap type. So Clara says, the sign swap each time with a Fibonacci number and a phi term. Yeah, I'm trying to be really careful to track the, so I've got this minus 1 to the n, which is technology I've used before for alternating plus and minus signs, because every time you give it another minus 1, it changes the sign. And the phi coefficient here, 1, 2, 3, that's this bit, so it's fn, because I was just on phi to the 4. Really hope I'm not out by 1, whatever. Okay, so it looks like you can do something with the index here to get this to also be a statement about fn and fn minus 1. And then this would be really magic. But once you've got two statements relating together Fibonacci numbers and the constant phi, something really ambitious you could do would be to solve those for fn, the Fibonacci number, in terms of phi. We've got two equations here and sort of two unknowns. If I shift the index a little bit, so maybe I change the left one to say phi to the n plus 1 is fn plus 1 phi plus fn, to just shift it to the next one. Then I've got two unknowns, fn and fn plus 1, sort of unknown, and I've got loads of phi's all over the place. Maybe I could solve those. Ah, yes, or suggestions in chat coming in now. Yeah, Trisha's got an explanation of my positive negative stuff. Yeah, I like that. If you multiply those two together, they should equal 1. Yes, I agree with that. And that's a statement about Fibonacci numbers and the number phi. I'm a bit worried by all my being out by 1. Am I brave enough to just do that? Let's do it and see. If I've made a mistake, then this will be wrong. But you know, you've got to take some chances. This is the Oxford Online Maths Club. For example, you might have the wrong pen selected. So something like this is true. I'm putting a question mark in brackets because my spidey sense says that my spidey sense says I have not survived the first 20 minutes without making any typos. Okay. Do I multiply this out? What do I want to do? Maybe. I kind of want to multiply both sides by minus 1 to the n. You can do that because, well, if this is 1, I'm multiplying both sides by 1. If it's minus 1, then I'm just moving the minus sign to the other side. And then I'll do some multiplication. What am I doing? Just multiplying terms together. Welcome to the Oxford Online Maths Club, where we'll be multiplying. I'm not very good at promoting the stream, promoting the show. Some would say I'm not very good at doing the show either, but you know, promotion is hard. You could be anywhere right now, but you're watching Fibonacci Facts. So here's a weird Fibonacci fact. You will need 3 Fibonacci numbers in a row, and the number 5, which is 1 plus root 5 divided by 2. And then this relationship. It's maybe true. This bit, this phi squared, I could write that as 5 plus 1. And then I'd get something really properly magic, right? Yeah, there's something in this. Good stuff. Yeah, good suggestion, Anonymous, to just multiply them together and see what happens. I'm going to leave this as a homework exercise to try and tidy that up. See if there's anything going on there. Maybe check if that's actually true, or if I'm out by 1. Okay. We've got a little bit sidetracked. We've done some Fibonacci numbers. We've got some phi facts. I want to pick up on the spiral in the song lyrics. So if you've just joined us, this episode is motivated by Australia's entry to the Eurovision Song Contest, which has some lyrics inspired by, we think, the golden ratio and possibly golden spirals. Yeah, so I was trying to work towards Binet's formula, right? Because we almost discovered it. Some relationship between phi to the n and phi to the minus n. Oh, which you've got as 1 minus phi, because that's something to do with 1 over phi to the minus n. And then there's this factor of square root 5 that maybe I was quite far away from rediscovering on screen. Spiral time. Okay, spirals. Because I've seen people talk about the golden ratio before, and usually when they're talking about the golden ratio, eventually they tell me something about shells. Here's a shell of a nautilus, image taken from Wikipedia. People sometimes tell me that this is an example of a golden spiral, and then they've got to explain what a golden spiral is. So I thought we'd do that very quickly. Oh, what exactly is the golden ratio? Golden ratio is just it's got this weird, it's just 1 plus root 5 over 2. That's what it exactly is. 1.618, some other numbers. That's its kind of, little sort of dirty secret, that it's just equal to this random surd. I don't think anybody has this, like, this is a dangerous claim. I don't think anybody has this surd tattooed on them. I think I'm back. Just one of those days. Chrome didn't shut down properly. No, it really didn't. Spiral! Right, where's chat gone? Okay, I'm going to wait for chat to tell me that I'm actually back. Anna says, oh, suspense. Want to know about the tattoo? In the middle of saying something absolutely ridiculous as well, which doesn't help. I think we're back in the same stream, so people watching the YouTube recording aren't even going to notice. Yeah, divided by 0, all very bad. I am back, thank you very much. We got chat on screen, we've got things where they need to be. Right, odds are I've broken something, and we'll only find out afterwards in the stream summary. Ooh, Teams has restarted, that is not good. I have a 20-minute pre-flight plan, a 20-minute checklist for things to do before the live stream. We have skipped 16 minutes of it in order to get this back online again. Let's see if anything goes wrong. What's the worst that could happen, right? What is the worst that could happen? Okay, so I was in the middle of telling you about spirals and the golden ratio, which is 1 plus root 5 divided by 2. There's this question about whether or not this nautilus shell, beloved of popular science, actually does a golden ratio sized spiral. So I suppose I need to show you a golden ratio spiral. I'll be brave, I'll do it in Miro, let's go. So golden ratio spiral, or golden spiral, is made out of quarter circles, and it works like this. So you have a quarter circle. I'm going to draw the whole circle because that's, I think, different and interesting. So you start with 2 squares next to each other, like this, and 2 quarter circles which are part of the same larger circle. So quarter circle, and the rule is that each time for the next square, you rotate by 90 degrees, and you resize so that the side length of that square matches onto what you previously had, the kind of previous diagram. So people usually draw this just with the quarter circles inside the squares. So now I'm going to take the largest one, copy it, rotate 90 degrees. It's quite fun rotating a circle by 90 degrees. And resize that so that it's not the same size as the previous square, it's the same size as the previous collection of squares along that side. So I need to make it that large and stack it together like that. So you see them spiraling outwards, square, square, larger square, larger square. Fans of the Fibonacci numbers will already have realized that in each case, the stack of the previous picture is, well, mostly the two previous largest squares. In particular, the height is the two largest previous squares. So in this case, I'm scaling this up, and the height of this new square is the sum of the previous two squares. So it's maybe not a surprise that the Fibonacci numbers come in. The Fibonacci numbers grow like the golden ratio. So you get this kind of nice Fibonacci golden ratio thing going on. I've never seen this with the full circles in before, so I feel like I'm contributing something to the pop science debate. Is that true? No, I have seen a lot of circles actually, now that I think about it. Now that I think about it, I've seen a lot of circles. Okay. So people usually draw this spiral. If I do something like this to sort of highlight it, quarter circle, quarter circle, quarter circle, quarter circle, and then, oh gosh, really large quarter circle, and then, oh, I can't even fit this one on the screen, really large quarter circle. I've missed quite badly. The idea is that this looks a bit like, well, lots of things. It's an example, almost, of something called a logarithmic spiral. Now, on a true logarithmic spiral, it's not made of quarter circles at all. It's made so that the angle between the origin and the point on the curve, that line between the origin and the point on the curve makes a constant angle with the direction of travel. The thing to imagine is that you are a hawk, and the hawk is spiraling inwards. So top-down view of a hawk. Tail, two wings, no, beak, there we go. Top-down view of a hawk. Oh, I need to move my hawk down. Okay. So hawk flies around so that its target, at the origin, makes a constant angle with its direction of travel. And it keeps that angle the same. You can do this if you have aerodynamics, so that you're flying in a particular direction relative to where you're looking, you spiral inwards along some sort of logarithmic spiral. So that's a good thing to look out for in nature. Anyway, so logarithmic spirals are all over the place. This particular one, with the Fibonacci numbers and squares and quarter circles maybe, and growing like this, it's called the golden spiral, and it's a particular example of a logarithmic spiral. Let me show you this Desmos plot that I've got. Pop. Pop. Okay, so Desmos plot. The general formula for these is something like, well, okay, so you've seen maybe exponential graphs, like a to the x, a to the power of x with exponentiation in there. If you do that wrapped around so that your independent variable is theta, the angle around, and your dependent variable is r, the radius from the origin, on a kind of, the thing that people draw sometimes is this kind of grid like this, where your graph paper is curved around. Your independent variable, instead of being x, it's theta as you go around, and your dependent variable, instead of being y, is r, distance outwards. So the grid lines here go round and round. Then what you can do is, as you change that parameter for what are you raising to the power of theta, you get these different spirals, like this. And there's a parameter that I can change. A parameter that I can change that changes how tightly spiraled this spiral is, like a kind of coiled spring that changes how that goes. Yeah, so these r and theta are polar coordinates, if you've seen those. The setting I've got for Desmos here is polar grid, which I'm going to turn off again, I think. The important thing is that there's some relationship between a dependent and independent variable there. Okay, the point I want to make is that all of these are sort of the same family of shapes called logarithmic spirals. And the one that you get from the Fibonacci numbers and those squares, or that growth rate, every quarter turn you scale by about the golden ratio, that's a particular example of this quite nice family of shapes. It's to do with, if you think of the hawk, the angle the hawk chooses between where it's looking and where it's flying. Okay, so you can actually try and do this to compare together. If you put one on top of the other and look to see what's the right number to put in, you see, well, the Nautilus isn't spiraled like this, and it's not spiraled like that. It's kind of somewhere in between. It's somewhere like maybe this kind of growth rate. Where do I want 1.2? 1.2 as the base down here, which is not obviously something to do with the golden ratio. And in fact, the actual golden spiral has a different number that goes down there, something to do with phi. So there's this kind of popular science thing to say, hey, look at this cool spiral. This is an example of a logarithmic spiral, and then to talk about the golden ratio. But in fact, shells in nature don't do the golden ratio. They do some different logarithmic spiral. Not all logarithmic spirals are golden spirals. Okay, that was the point I wanted to make about spirals. People do get very excited though about the particular golden spiral, this one, with the squares in and the quarter circles. I've seen people post on the internet when they see something that looks a bit like that spiral to say, look, nature's beautiful, nature keeps inventing this golden spiral. In particular, the internet seems to like doing this with cats. So I found two examples. On the left, you've got to cite the cats, right? On the left is Waffles the cat on Facebook. So if you're on Facebook, then you can, I guess, follow Waffles the cat. Here's Waffles the cat in a box and also in a golden spiral. And on the right, a cat called Katana on LinkedIn. So I was a bit surprised to find logarithmic cats on LinkedIn, but you know, all sorts on LinkedIn. This one's quite, I think the one on the left is less convincing than the one on the right, and neither of them is that convincing, but they both have pictures of cats in, so that's nice. I'm still setting up things. Oh, I've missed loads of questions. Why is it called the logarithmic spiral? Oh, it's got exponentiation in it. Oh, sorry, I really missed a load of things. Yeah, I've got chat underneath something else. There we go. Why are they called logarithmic spirals? There's an exponential in there hiding behind the scenes. So you could take the logarithm of both sides and rewrite it in this equivalent way, where instead of saying that r is the dependent variable, you could phrase it so that theta's the dependent variable, in which case everything would be inverse and it would be the logarithm that appears. There's a log function in there, I suppose. That's not a great reason, but I think that is why it's called the logarithmic spiral. What does it look like in normal coordinates? Oh, normal coordinates, that function is just the standard a to the x graph. No spiraling around. Normal coordinates are kind of boring. They just go on forever in each direction along the x-axis. Whereas theta has got this kind of interesting behavior where you go round by 360 degrees or 2 pi radians and you get back to where you started. I learned polars today. Hey, yeah, you make all sorts of graphs. I would encourage you to type e to the theta into that. Oh, look, chat's lovely. Chat's just lovely. It turns out I can crash. I can crash and go away. When I come back and people are just nicely talking about functions. Good. Have I remembered to unmute? Yes, I have. You'd have told me if I'd forgotten to unmute. Approximately once a year we have one big technical issue, and it's nice to know that I've got it out of the way. Anyway, so we were talking about spirals because of spirals in nature, and sometimes people maybe being too keen on golden ratio. I think spirals are interesting in their own way. I'm not sure that galactic spirals have anything to do with the golden ratio. I'm not even sure they're logarithmic spirals. I thought I'd talk about spirals a little bit because that's fun. And there's this number 0.618 in these song lyrics as well. If you've just joined us after the crash, we're analysing some song lyrics on the Maths Club today. This number 0.618, which we've dug into. First I said it was phi minus 1. Someone in chat told me it's 1 over phi as well, so that's pretty nice. We have these relationships between powers of phi. But I wanted to show you one last thing, because I'm not the first person to analyse this, of course. In fact, I became aware of this from a review that I read. So here's Alex S8ep3's review of the song, and I've bolded the bit where that journalist has a go at explaining the golden ratio. So they say the artist is not talking down to the audience. The lyrics are based on non-integer positional numeral system, the golden ratio base. So I read that in the review and I thought, the what? Because I've never heard of the non-integer positional numeral system, the golden ratio base. And then in the song lyric, I can see 0.618. Lovely. So part of what I wanted to explore today is, what is a non-integer positional numeral system, the golden ratio base? Because there's no way that that's something the journalist has just made up, right? It's a sequence of words that you wouldn't just string together. But I thought they would just say the golden ratio. They've said, no. James has missed something here. James has missed that this is about the non-integer positional numeral system, the golden ratio base. What do we know about these things? I've got an arrow going off to the left, but just to quickly point at things. Non-integer, that's all right. I know what integers are. Non-integer, so not an integer, fine. Okay, most things are not integers. Positional, pass. And then numeral system makes me think of like binary or decimal. Those are numeral systems. So positional, no. I don't know what it would be to positional. And then it says base at the end as well. And that's like how this is. So this is like base 2 and this is base 10. And then I kind of realised what they were talking about. The thing they're talking about in bold, maybe you've got there as well, is the idea of having a base system for numbers to write numbers in terms of phi. Like how we currently write numbers in terms of powers of 10, or to write numbers in powers of 2 for binary. What if we used phi instead? And that's a really weird idea. I love the idea that the song lyrics are about that. I'm not sure they are, but I think maybe they just mean to say golden ratio. But I would love the idea that the song lyrics are about that. Hi Anonymous, sorry you're not well. Goodness me, get well soon. You missed the biggest technical crash of the year. So then I looked up the non-integer positional numeral system, the golden ratio base, and I found a Wikipedia page explaining how you can use powers of phi to make a kind of number system like decimal or binary, but base phi, which is obviously, and I should have seen this coming, it's obviously known as finery. So just in the 10 minutes we've got left, I want to give you a very quick overview of finery. It works like other numeral systems you might have seen. There's a units position, so let's go units. So you can write the number 1 in finery just as a 1, but then this number here doesn't represent 10, and it doesn't represent 2, like it would in binary, where this would be 1 lot of 2 and no 1s. This represents phi, the golden ratio. So in the finery system, this is how we write the number, like 1 plus root 5 over 2. Which is, I guess, good, because 1 plus root 5 over 2 is loads of writing, whereas 1, 0 is not very much writing at all. Base phi uses digits 0 and 1, so it's not anything else going on there. Further to the left, the numbers mean phi squared and phi cubed, of course. And to the right of the finery point, there's a 1 over phi position. Like how in decimal there'll be a 1 over 10, or in binary there'll be a 1 over 2. I'm not sure if people have seen the binary point and things to the right-hand side of the binary point, but hey, that's how it would work, I suppose. So over here would be 1 over phi squared. Now, there are some consequences of this slightly mad decision. It's not immediately obvious that you can write sensible numbers using this system at all. I mean, we're good for powers of phi, and I guess sums of powers of phi, but not immediately clear that we can write any of the counting numbers, for example, using this system. We can, I'll show you how in a moment. Other things worth noting. So, here we go. We have facts like this, that phi squared is phi plus 1, which in finery becomes the statement that 100 is the same as, I'm writing way over there, is the same as 11. So in finery, 11 means 1 plus phi, and phi squared is written as 100, and those are the same. This is a bit awkward, and in fact, you can do something similar. Have I got that the right way around? I think I do. Nobody's going to use this to build anything with finery, are they? This is going to be fine. I'm going to keep going. You can do something similar with other powers of phi. Yeah, I've lost slightly where I was going with this. Was I going somewhere with this? Oh yeah, so phi is 1 plus 1 over phi, of course. So if you have a 1, 1, you can kind of simplify by switching it out for a 1, 1, 0, 0. It'll be fine on the night. Yeah, this base has non-unique representation. It has quite a lot of non-unique representation. If you like, 1 over phi is a little bit bigger than 1 over 2. So you get some sort of redundancy. It's only using the digits 0 and 1, which is the same as what binary uses. Binary does that very efficiently. With finery, the kind of building blocks are a bit larger. So if you like, there's a bit of overlap. You get some redundancies in the system. Yeah, okay, so 0.11 means 1 over phi plus 1 over phi squared, but that's just the same thing as phi plus 1 over phi squared, which is the same thing as 1, right? I'm really second to, you know, that's the same thing as 1. So this means is 1. And in general, whenever you've got two 1s in a row, you can simplify. So there's kind of this redundancy that if you have two 1s in a row, that you can simplify that to something else, which sounds like a weakness, but could be a strength. On Wikipedia, I saw a link to one sort of encoding that I don't really understand. Something about data transfer, where you want a bit of redundancy in your data signal so that if something's corrupted, you stand a chance of spotting it. And if you sent all your numbers in finery instead of binary, then that costs a little bit. The numbers are a bit longer. But you get some built-in redundancy along the way, because if the person receiving the number sees two 1s in a row, they know, person I'm communicating with would never miss an opportunity to simplify two 1s in a row. Therefore, there's been some data corruption right here. I just mean redundancy in the ordinary English sense that you can afford for some things to go wrong and still make your point. There's a whole science for this around things like error correcting codes, where if I need to send you a number over the phone, I could for security, to make sure you receive it, I could just say it twice, or I could say it 3 times. But can we do something more efficient, where maybe I send you the number, and then I also send you the sum of its digits? Sometimes that's called a checksum, for you to check that the sum of the digits matches up. And if it doesn't, then you know that something's gone wrong. And that's a bit more efficient than me repeating all of the data, because I just have to send a little checksum. That sort of redundancy is what I mean, the kind of maybe ability for you to notice that something's gone wrong. Okay, this is finery. It's got adding. You can do adding, you have to do a lot of carrying, and then you have to do some simplifying. It's, if I'm honest, a bit mad, but you know, golden ratio, worth it. So I'm very pleased that I learnt about this week, because it's called finery, and it involves the golden ratio, and I had never heard of it before. I found out about it because it was in a review of some song lyrics. I'm not sure the review is an accurate summary of the song lyrics. The song lyrics have 0.618 pow in them. The song is from Eurovision, which I love. This was Australia. The footage I showed you at the start is from the first semi-final. Sadly for Australia, there will not be a final performance because they didn't qualify for the final. And what I've actually done is base an episode of the Maths Club around a song that isn't even qualified for Eurovision this weekend. So maybe it's not as topical as I thought. Anyway, second semi-final is on tonight. I don't know if any of the lyrics have got maths in, but if you're into that sort of thing, you could have a look at that. And then the finals on Saturday. Oh, I need to tell you how to write integers in finery. Oh my goodness, yeah, absolutely. Can't get away with that. So a good strategy for this. How can I do this? A good strategy for this. Perhaps if I can write the number 2, then you'll believe that I've got something here. For example, okay. I can do it, but only if you believe that I can simplify carries. So 1 is 1 over 5 plus 1 over 5 squared, and then 2. What I can do is square that previous thing. And this is not quite okay. This is not quite okay because I've got to do something about this 2. 2 over 5 cubed. I've kind of got to carry because in finery you only have the digits 0 and 1. But this is an indication that we're along the right lines to get something that's like this expression in powers of phi. I've got to resolve the carry. How on earth do I do that? Oh my goodness. It's all coming together. Okay, I had an expression earlier for 1 over 5 cubes, didn't I? I need to take 1 of the 5 cubes and replace it with something else. But my expression for 1 over 5 cubes also involved the number 2, didn't it? I can't remember. 1 to the 2, not 2 to the... 1 to the 2, not 2 to the 2. Isn't it annoying when someone else has the best chat? They didn't qualify for the final. That's amazing. Suddenly thought about representing complex numbers using phi. I don't think I'm going to recommend that. So I'm going to leave this on screen as like deal with this. You know, just deal with it. And then from there, wait, what have I done? Oh my goodness. Thanks, Rory. I even read your message out. I read your message out of telling me that 1 squared is, oh my goodness, 1 squared is 1, not 2. Okay, it's been one of those days. Ah, brilliant. That's genuinely great. Here's a great way to write the number 2. The number 2 is equal to 1 plus 1. Welcome to the Oxford Online Maths Club. 1 plus 1 is 1 over 5 plus 1 over 5 squared. So one way to write the number 2 is to have 1 plus 1 over 5 and a 1 over 5 squared. You can deal with this a little bit. So this 1 plus 1 over 5 is equal to phi, so you could write that as this. to simplify to the left. So when you see 2 consecutive ones at the start here, you can simplify by kind of carrying that over. And then it's just a case of adding 1 again. So adding 1 looks like this. And then adding 1 again, I think for the next one, oh gosh, I need another expression for 1, so I need some other way of dealing with this. Oh, I could simplify this, couldn't I? So I could carry this over, or 100, and then I can keep going. So that's all nice. Good, okay. Yeah, because now if I go 101.01, it's 4. The trick was to add 1. As we often say on the show, 1 plus 1 is 2. Welcome to this. Keep bumping the ones up. Yeah, I should keep going. Eventually you'll run out of these. Yeah, now everyone in chat is piling on a bit. Right, okay. We've had a strange live stream. Let's do a vote at the end. That sounds like fun. I fully know what's going to happen here, but like, come on chat, let's do the funny thing. Hey, after seeing an hour of phi and finery and Fibonacci numbers and golden spirals, I wonder if that's changed your opinion on the golden ratio in comparison to E and pi. Bearing in mind it's not a fair fight because we haven't talked about any fun properties of E or pi. I think this was the closest that we got to like some hardcore mathematics today. I really want to see if people can work this one out. That's good homework. While you're voting, I'm going to review, quick performance review. That's kind of convincing. It kind of looks quite a lot like the seashell actually. That's good. Cats, everyone likes cats. Good. I think the cat would look more like a spiral if it wasn't in the box. If anything, this cat looks like a rectangle because it's in a box. I'll just draw the rectangle on, and then hey, that's quite a nice rectangle. There's this whole field where people think that maybe a rectangle with aspect ratio phi looks nice. So I'm not sure how I feel about that. People have voted for phi. Oh, that's very kind of you, chat. There you go. A win for phi ahead of pi and e. Maybe future episodes can deal with the other sides of that triangle. My goodness. Okay. Thank you for watching. Next week we do genuinely have a computer science takeover lined up. So we've got a couple of episodes where we've got some computer science topics coming along. That'll be, I think, especially interesting for anybody who's interested in maths and computer science, but also everyone else. It's a chance to see some other material. This is what happens when I make up the material. Let's get some other people involved as well. I will see you next week. Yeah. Oh, right, catching up. Pentagons look really nice and they have fine. We have a previous episode about pentagons. Gosh, I think it was about a year ago. We looked at the geometry of the pentagon. Can't remember what we called the episode, but if you go through the back episodes, there's some pentagons in there. We will see you. Final phi joke, you got it just above the line. We will see you in 167 hours for another episode of the Oxford Online Maths Club. Stay safe, have a good evening, have a good weekend. Take care, bye.